For analyzing our lab, you should, at this point, have a graph that you have made of circumference as a function of diameter. You should have drawn your best fit line, picked 2 points near the end that were not data points, and used them to calculate a slope. And then I asked you to find an equation in terms of y equals mx plus b form, and so you should have done that. And so hopefully that is review, but just in case it's not, very quickly, slope is rise over run, so the change in the y value over the change in the x value. So I took my two endpoints, subtracted my y values, subtracted my x values, divide, and I got a slope of 3.13. So that gives me my m, my slope. To find b, I now pick one of my two data points one of my points that was on my trend line. And plug the values in. So I did my 2.4 and 8.0, so my y value, 8.0 equals my slope that I found, 3.13 times my x value, 2.4, plus b, my y-intercept. And then we just solve for b. So 8 minus 3.13 times 2.4 is going to give us 0.5. And so my equation becomes y equals 3.13 plus 0.5. And of course, your equation is not going to be exactly the same as mine because your data was not the same as mine, and even if it was, you probably didn't draw your line in exactly the same place. But you should have an equation that looks something like this. And so the first thing I want us to do is take and just copy your equation, whatever it is, into the next available space in the lab part of your notebook. So I told you to put your lab stuff at the back. So put that in the lab part of your notebook. Oops, 3.13. Oh, I see my mistake. Should be 3.13x. Y equals 3.13x plus 0.5. So y equals 3.13x plus 0.5. And now what we want to do is figure out what is this actually telling us? What is the significance of all of this stuff? And so we know that our y value, if you look at our graph, what our y value represents is the circumference. And the x value was the diameter. So that makes sense. That's what the graph is telling us. The circumference is something times the diameter plus something. So then we want to figure out what is going on with these two numbers. What is the significance of those? Are those supposed to be some sort of constant, or they depend on a particular situation? And so if we were all in class, I at this point would have everyone shout out what number they got for their slope. And we'd hear a bunch of numbers. I got 3.13, 3.05, 3.22, 2.98, 3.20. And then once we'd shouted out all those numbers, I would ask, what's the significance of all those numbers? What do they all seem like they're close to? And at this point, usually several people would shout out pi, and one person would shout out really excitedly 3. And it is true that they're close to 3, but they should on average be closer to pi. And so our slope is about pi. And a way you can actually experimentally determine pi is defined as the slope of this graph. It's the thing that connects diameter to circumference, and you can experimentally determine what pi is by doing this lab. And the more data points you have and the more carefully you do it and the better your trend line is, or the more times you repeat the lab and find the slope and average it together, the better value you would get for pi. And then, of course, with the advent of calculus and figuring out like infinite series that add up to pi. There are now ways to compute pi, but in the beginning, this is how people would have actually figured out pi. They would have actually performed an experiment, and the most precise way to actually figure out pi, sort of by hand, by measuring it, is to find the slope of this graph. The other value, the y-intercept, I would have everyone shout out what they got for this. Again, we'd hear a bunch of numbers. This time, though, like I got positive 0.5. We might hear someone say negative 0.5. Someone might have gotten exactly 0. And I'd look at them and say, did you really get 0? Did you force it to go through the origin? And I could go either way. A bunch of people would shout out, other numbers, 0.1, negative 0.3, positive 0.4, negative 0.1, positive 0.3, negative 0.6. And then my question would be, so with all those numbers we just said, what does it sound like they're hovering around? What does it sound like their average is? And if about half of them are positive, half of them are negative, and they're all pretty small, and when I say small, I mean small compared to our measurements. And so if this is a y-intercept, 0.5 is small compared to all of the y values on our graph. If they're all small and about half are positive and half are negative, it sure seems like that is supposed to be 0. This is about 0. And as we collect more and more data and as we collaborate between different people or different lab groups, we can get more and more precise values for different relationships that we're going to study. And in this case, what we find is this particular relationship, that circumference is equal to this number that's the average of all the slopes we're going to get, or the slope we would get if we did like thousands and thousands of really carefully done data points. It's 3.141 whatever, and we gave that the name, we have the name pi for that, but it turns out to be pi times the diameter. Plus nothing, plus 0. And so if we think that it's supposed to be 0, and this is just off by a little bit because we can't make perfect measurements, we can't draw our line perfectly, it's not necessarily going to go to exactly 0, but if we did the experiment enough times, everything would sort of average out to 0. If it's supposed to be plus 0, we don't need to write plus 0 on here. It's not going to change anything. And so we get this equation. Which is, of course, should look familiar. It is probably something many of you recognized is what was going to happen. We were going to find that the circumference is equal to pi times diameter. But once upon a time, no one knew this. Sometime, would have been probably thousands of years ago as far as like finding pi for the first time. But no one knew this relationship. And someone observed, hey, if I have a circular object, there seems to always be this constant relationship between the diameter and the circumference. And I wonder if I can quantify that relationship. And the way that a long time ago people would have originally come up with the value for pi in this relationship is by doing this sort of experiment. And we can use a graph and use the slope to find those values. And so this is going to be something we do in physics all the time. When we are trying to figure out new relationships for stuff that you don't already know from geometry class, we're going to go into the lab and we are going to measure stuff, put it on a graph, try to figure out what the relationship is, and then figure out how is everything connected. What is the significance of any constants that appear in our equation? Are they related to some parameters of the experiment, or are they the same no matter where in the universe or how in the universe we do it? And we'll be able to generate all sorts of equations, not only like this, but also significantly more complicated ones. We can also use experiments to go in the opposite direction. We can use an experiment to check an equation. So if we have an equation that we believe is true, that we've come up with from some sort of experiment, like say we said, hey, I think circumference is equal to pi times diameter. Well, how could I check that? Well, the way that you would check that is by doing an experiment. This is one variable is equal to some constant times another variable. Well, that should form a straight line. That should be a y value is equal to some slope times an x value. And so if this equation is true, if our geometry teachers didn't lie to us, we should be able to prove this equation by graphing circumference as a function of diameter and getting a slope of pi if the equation is true. And so we will both use graphs this year to determine relationships and use graphs to determine relationships. To verify relationships. The one other thing that we should do with this data is that anytime we find some sort of like physical constant or think we've measured something or get a particular result where we know what the answer should be, something that is frequently useful for describing the quality of your experiment and figuring out did you actually prove what you think you wanted to, is to calculate a percent difference. And so for the percent difference, between our slope and pi. The way you find the percent difference is always the difference between your theoretical value and your experimental value. We're going to take the absolute value of this, so the order you subtract in doesn't matter. So pi minus 3.13 divided by the correct value, the theoretical value. So it's theoretically supposed to be pi, so we're going to divide by pi. So you could either use the pi button on your calculator, or if we just write it out, 3.14, 3.14159, however far you want to go. We should at least use as many significant figures as we have in our slope. So 3.14, 3.13, good enough, divided by 3.14. 100%. Since it's going to be a decimal, I want to convert it to a percentage. That's going to be, well, that's pretty good, 0.3%. And so I figured out that